Hello geometry students, my name is Jami Emigh, and this video is our discussion on section 5.2, bisectors of a triangle. When three or more lines intersect at one point, they are called concurrent lines. And the point at which they intersect is called the point of concurrency. Let's see if we have a figure to look at here. Oh, that's let me just sketch these lines would be concurrent lines because they intersect at one point. And then this right here would be the point of concurrency. All right, so let's look at those inside of triangles now. Here we have three concurrent lines, and their point of concurrency has a very specific name, okay? If the three concurrent lines are perpendicular bisectors of the triangle, then that point of concurrency is called the circumcenter. All right, if those three concurrent lines are the angle bisectors of a triangle, then that point of concurrency is called the incenter. If those three concurrent lines are the medians of a triangle, then the point of concurrency is called the centroid. And last one, if those three concurrent lines are the three altitudes of the triangle, then that point of concurrency is called the orthocenter. And you're going to need to remember these terms. You may have questions that just say, find the incenter. And so you'll have to know, okay, the incenter is the point of concurrency for the three angle bisectors. So you'll need to know that the incenter relates to angle bisectors, the centroid relates to medians, and so on. Now let's make sure you know what perpendicular bisectors are, angle bisectors, medians, and altitudes. All right, so first one, perpendicular bisectors. You take one side of a triangle and you cut it in half with a perpendicular line. Then if you could twist this, it would be easier, but here's a side of the triangle, and you cut it in half with a perpendicular line. And then the third side, you cut it in half with a perpendicular line. Those are called perpendicular bisectors. Angle bisectors. So you go to one angle of the triangle and you cut it in half. Go to the next angle of your triangle, cut it in half. Go to the next angle of your triangle, cut it in half. Those are called angle bisectors, and they meet at the incenter. Okay, a median. A median, you go to a vertex of the triangle, and then you go to the middle of the opposite side. Okay, from here to the middle of the opposite side, hence the congruent tick marks there. Go to an angle, and then the middle of the opposite side. Start at an angle, go to the middle of the opposite side. That's the definition of a median. Well, let's see, next one, altitudes. So you take one side of your triangle, so focus on this side first. Focus on this side first, pretend it's your base. And you go straight up with a perpendicular line to the highest point. That's the altitude. Now this one's a little tricky to see. If we could twist the triangle, it would be a little easier, but focus on this side now. Pretend that's the base of your triangle. So if that were the base, let's say that side was on the ground, then the height of the triangle, or the altitude, would be straight up, vertical line that goes to the tallest point of the triangle. And then last one, okay? If you focus on this side of the triangle, if you could twist it to make that on the ground, it'd be easier to see, but I don't know if you can twist yours or not, depends on what you're looking at. But if you go straight up with a vertical line to the tallest point of the triangle, that is an altitude. So there are three altitudes in every triangle, three medians, three angle bisectors, and three perpendicular bisectors to every triangle. They are all concurrent lines, and their points of concurrency have specific names that you're going to want to know. Okay, perpendicular bisector of a triangle. So we're going to break it down here. The point of concurrency is called the circumcenter because it is the center of a circle circumscribed about the triangle. Okay, so if we were to, let's see if I can do this. Not too bad. Okay, so that right there is a circle circumscribed about the triangle. So it's on the outside of the triangle. Just picture taking your triangle, putting it inside a circle, and maxing out, then like making the triangle as big as you possibly can. Okay, all three vertices touch the circle. All right. Oh, there's a much better drawing. Okay, so if you have your three perpendicular bisectors, like we have this point of concurrency right here, is the center of that circle, which makes sense. I mean, look at the radius, all three of these radiuses, any radius. I mean, you can draw more. These all have the same length. But what's important for us to see is that these three segments have the same length. Okay, so if you have an acute triangle, it works out like we've been sketching there. The circumcenter of the triangle will be on the inside of the triangle. The three perpendicular bisectors will meet on the inside of a triangle if the triangle is acute. The circumcenter of an obtuse triangle, however, will be on the outside of a triangle. And the circumcenter of a right triangle will be on the hypotenuse. Right there, on the hypotenuse. Here it's outside of the triangle, here it's inside of the triangle. Oh man. All right, concurrency of perpendicular bisectors theorem. The perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. That's what, here, let me erase some of the sketcher. That's what we were looking at right here. That's this theorem. The perpendicular bisectors of the sides of a triangle are concurrent at a point that is equidistant from the vertices. So these blue dashed lines, those are all congruent to each other. They have equal length. All right, the challenge might be making sure you don't mix up the perpendicular bisectors and the distance from their point of concurrency to the angles. So let me just emphasize one time here that the red lines, those are the perpendicular bisectors. The dashed blue lines are just showing that that point of concurrency is equidistant from A, B, and C. Okay, so using the circumcenter of a triangle, how many segment lengths can you find? So looking here, they've given us 7 on the bottom there, a 6 right here, and this distance they gave us as 8. So go ahead and pause this video and see how many more segment lengths you can find. Welcome back. Let's see how you did. If you put an 8 here and an 8 here, great job. If you put a 7 right here, that'll work. We know that much. Anything else we can find? That 6 is not congruent to anything else. Well, we could use the Pythagorean theorem to find more segment lengths if we wanted to. Like for this triangle right here, that's a right triangle. We have lots of right triangles in this figure, so we could do lots of Pythagorean theorems. if we were trying to find this segment length right there, it would be, I'll just leave it as question mark, that segment length squared plus 7 squared is equal to 8 squared. So that segment in question squared is equal to, that would be 64 minus 49, 15. So that segment would be equal to the square root of 15. And there are no perfect squares inside of 15, so we can't reduce that any further. We could approximate it though. If we do square root of 15, it's approximately 3.87. Okay, that makes sense. This one's 6, this is 3.87. So you could do that to find more segment lengths. You have lots of right triangles in there, so you might even be able to find all of them. But the point of using the circumcenter was to recognize that all 3 of those blue dashed lines are 8 linear units. Okay, so to find the circumcenter of a triangle, we can put the triangle into a rectangular coordinate system like you see here. It is at P, O, and S are the vertices. And if we can construct at least 2 of the perpendicular bisectors, we'll find where they meet. We know the third one will meet at the same point, so we don't have to construct all 3. We can do this with just constructing 2. So which 2 would be the easiest? Well, this one would be one of the easiest to construct because it's cutting that vertical line in half with a perpendicular line. So this side is 1, 2, 3 units, and this side is 3 units. So see that? Focus on that vertical segment OP. If you cut it, it's 6 units long, so you would cut it right at 3 with a perpendicular line, which is easy to do because that segment OP is vertical, so our perpendicular line would be horizontal, which is why the rectangular coordinate system makes that one easy. Now let's do the bottom one, segment OS. That is 4 units long, so if you cut it at 2, then this side is congruent to this side, and this vertical line would cut that horizontal line in half, and they're perpendicular to each other. So we're really done. We have found the circumcenter of the triangle. It's right here. It's at looks like 2, 3. If you were to cut the other one with a perpendicular bisector, well, we know this segment is equal to this one already. The trickiest part would just be trying to make sure it's perpendicular. So if you, maybe like that, that looks perpendicular. All right, an angle bisector of a triangle is a bisector of an angle of the triangle. So every triangle has 3 angle bisectors, and the theorem says that the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides of the triangle. So again, let's not confuse the red and the blue lines in this figure. The red lines are the angle bisectors. The blue lines are showing that this point of concurrency is equidistant from all 3 sides of the triangle. So we have 3 congruent segments there with as far as the dashed blue lines. The point of concurrency of the angle bisectors of a triangle is called the incenter. The reason for that one's name is because it is the center of the circle inscribed in the triangle, and it is always inside of the triangle. So you don't have to worry about, oh, it's acute, therefore it's inside, it's obtuse and it's different, right is different. The incenter is always in the center of on the inside of a triangle. And so this is a circle inscribed in the circle. Remember our last one was circumscribed about the circle. That's when you're on the outside like that. Just think of maybe taking a circle, putting it inside your triangle, and then just maximizing it out until it's touching all three sides, and that will make it inscribed. All right, so let's use that theorem, the knowledge of the incenter being equidistant from all three sides, to find some missing parts of this triangle. All right, well, we are told that GE equals, or can be expressed by the algebraic expression, twice whatever x is less 7. GF can be expressed as whatever x is plus 4. And they're asking us to find GH, so this distance here. Okay, so I'm going to highlight there are 6 segments inside of that triangle. I'm going to highlight the 3 that are the angle bisectors first. That is, this one's an angle bisector, this one's an angle bisector, this one's an angle bisector. Okay, so those are the 3 angle bisectors. This point G would be called the incenter. And I'm going to use blue and I'll make them dashed so it looks like the theorem. These represent the distance from the incenter to the sides of all 3 triangles. And the theorem told us that those 3 distances are equal to each other. So we can write an equation. We can set any of them equal that we want to. We have 2 of them that have expressions, so we can set the x plus 4 and the 2x minus 7 equal to each other. Minus x from both sides and add 7 to both sides, and you get x equals 11. So GF is 15 units because it's whatever x is, which we know is now 11, plus 4 more. And if GF is 15 units, then all 3 of those, GF, GE, and GH, are 15 units as well. So we were asked to find GH, and it is 15 units. And that will conclude our discussion on section 5.2. My name is Emigh. Thank you for joining me, and I will see you next time for our discussion on section 5.3.